right, coming back again to SRTM, now we have Michal, and he will be talking about more trust in your BIOS.
Thank you for attending my talk, and hello. I would like to present you my recent work about the static root of trust for measurement that I have implemented with core boot, vboot TPM, and a permanent SPA flash protection. I am a firmware engineer at a Polish-based embedded consulting company, 3M Dev, and I'm most interested in advanced hardware features in core boot and various security solutions. So I will briefly describe what the SRTM is, how it is implemented in core boot, and describe each of the components. And I will also present what other additional features I have added to the firmware to make it better and more customer-friendly and user-friendly. Of course, I will show some small demo, how it works, and describe some future improvements that can be made in my implementation. So, what the static root of trust for measurement is? It is a root of trust that is based on a piece of immutable code. Each root of trust requires to be set up with its own core, which is a basement of the whole chain of trust. And we call it the core root of trust for measurement, also CRTM, so an abbreviation. And in core boot and other measurement systems, it is realized as a self-measurement which is placed in this immutable piece of code. This self-measurement is the base for all other measurements and verification of next executed components. This immutable piece of code can be achieved via various mechanisms, which can be based on SPI flash block mechanisms like hardware protected mode, which I think most of you already know about. It is a right pin protect screw, right protect pin protect screw, for example, or a jumper. Or there is also a one-time programmable mode available on certain SPI flash chips that allows to permanently flash the status registers on the SPI flash. There are also some silicon vendor-based solutions like AMD hardware validated boot, which is based on the PSP boot ROM and only does allow to boot cryptographically signed components in the early boot phase. And the Intel Secure Boot or BootGuard, which is also based on the AMI or TXC boot ROM, which also serves the same purpose as AMD hardware validated boot. It does not allow to execute unsigned code in the very early phase. And first of all, why did I even attempt to implement this, even though there is an implementation for all of this almost in the core boot? So this was mainly aimed at our customer needs, who would like to have a firmware that will not allow to execute unsigned components and would have be able to attest its own firmware with, for example, the measurements that I made in the firmware. So the advantages of the SRTM are basically the measurements that are stored securely in the TPM, and which can be later used for the attestation in the OS. Those measurements can be also used to, for example, seal some secret data like disk encryption keys, and only the trusted firmware state or trusted platform state, I would say, can allow to unseal the secret, for example, to unlock the disk. And the verified firmware feature can also prevent from executing an unsigned component in the firmware. So how does the SRTM look like in core boot? So verified and measured boot mode are available since February 2019. And the implementation was brought by Zolin, or known as Philip Dippenwiese, also, which is an organizer of this conference. And basically comprises the following components. From the first component, and most crucial, is vboot, which is Google's verified boot reference implementation. The TPM driver, which is responsible for all whole low-level access to the TPM. It's a part of coreboot code base. And the flash map, also developed by Google on the needs of their Chromebooks, which allows to describe the firmware image differently than coreboot did it before. So flash map has this advantage that it can allow to have multiple coreboot file system inside. So we can have like multiple firmware stacks in one image. And what is most important, everything is open source. And my implementation is based on PCNG's APU2 platform. The TPM module is Infineon, SLB, as presented on the slide. And the flash chip I have used to implement the permanent SPA flash lock is from Adesto. It's an 8 megabyte chip. This is how my firmware image looks like. This is a diagram that describes the flash map layout of the image. And it basically contains basically contains 3 parts that should be mentioned. And the write protected read-only legend is 6 megabytes in size. It contains the boot block, so the reset vector, the flash map layout description, the ROM stage where the RAM is initialized, and the Linux kernel, which I will describe later. And in the read-write sections, which are updatable, contains also core boot stack, beginning from RAM stage and payload. And I have also some miscellaneous read-write region, for example, for PSP firmware, and where I store, for example, the boot order or vital product data. So a little bit about Google's vboot. So it was made to make the verified boot happen on the Chromebooks. Their idea behind that was to have a root key, the public part of root key, stored in a structure called Google binary block, which was then used to verify the firmware signing keys, which signatures of the code that is signed by these keys is in the V blocks in read-write firmware. And also Google wanted to have the update procedure to be safe. That is why they also implemented the 2 read-write partitions. So in case one partition is being corrupted or has garbage or the firmware is broken there is also a backup firmware partition B, for example, which can be booted with older but still working firmware. And the vboot also provides all the cryptographic algorithms already. What's different in my implementation than in Google's? In Google's Chromebook, the root of trust, which was in the SPI flash and the self-measurement, was protected by few block protection bits of the SPI flash, along with hardware protected mode, which I mentioned earlier. So one has been locking the status register and additionally protecting it with a write protect pin, with a screw or with a jumper, typically with a screw. But in my implementation, the lock is permanent, so it is independent of the write protect pin state. And Chromeboxes or Chromebooks recovery mode used external USB to recover the operating system, not the firmware. In my implementation, I have put a minimal Linux kernel into read-only to have a friendly shell environment with a few necessary binaries like flash ROM and some network drivers, storage drivers, just to get the firmware from some external sources the trusted firmware and flash it back in case the read-write partitions are untrusted. And that's how the boot process look like. So we have, as I mentioned, the boot block and ROM stage with RAM initialization in the read-only firmware. In the ROM stage, there is executed the vboot logic, which decides which partition we do like to boot, and of course checks the signatures of the read-write partitions. And in case these partitions are not valid, it boots to the read-only line stage and then the recovery kernel. Or if the partitions are valid, it boots normally with RAM stage and cBIOS payload and to the target operating system. The TPM driver Coreboot, which is used in the SRTM implementation, is located in the source security TPM directory and covers both TPM 1.2 and 2.0 modules, and is responsible, like I said, for the whole low-level access to the TPM. It is mainly used in the vboot logic, which is implemented in the source security vboot. This directory mainly focuses on the hooks that need to be made to the vboot in order to enable the verified boot mode. And there are two files that need our attention. It is vboot SRTM, which contains the initialization code for the vboot measure boot mode. It initializes DPM, vboot context, and does the self-measurement of all the components that we have already executed, and the measurement of the glue binary block, which is extended to the PCR0 and is the core of the root of trust. And there is also a vboot measured CBFS hook function in the vboot SRTM, which is a hook that during an executable component execution, it invokes a hashing algorithm, which calculates the hash of the component and then extend it to the PCR before it is executed. And the whole vboot logic starts at a program location. Typically, it is RAM stage or ROM stage when we have a platform that supports the environment boot. So the main issue I have encountered from the start was the default SPI flash chip that was present on the APU2 platform. This WinBond also has the one-time program mode available, as the datasheet states. However, there is a small note there that say that this mode is only available upon special order. So probably I would have to order thousands of chips to get those mode working. Either look for another SPI flash part that would do it out of the box without any special orders. And I fortunately found it. I found a desktop chip, which has surprisingly the same instruction sets, the same registers, and everything. And moreover, has the SPI one-time programmable mode available without any restrictions. Please note that this one-time programmable may not fit everybody, since it was mainly aimed to protect our customers' firmware. So not everybody may want to lock permanently their firmware and get stuck with some bugs if there are any in the locked sections. And my additional value, which I have added to the SRTM, is boot order region. Because with multiple CBFSs, we cannot determine which partition we should check for the boot order file, which is utilized for cBIOS, to prioritize our boot medias. So I have made a small region in a flash map that where I store the boot order entries, and made the cBIOS read it instead of CBFS file like it was previously. And now, thanks to that, I have a persistent boot order. As I mentioned earlier, I have put a minimal Linux kernel to the read-only flash part. I had about 4 megabytes left space there in read-only, but I managed to put inside a minimal Linux kernel with only a few kilobytes left. The kernel was built based on the heads repository. I just cut off some unused modules and put only some flash ROM, CBMM, and GPG, for example, for signature verification and basic network drivers and remote storage drivers. And I've got a nice recovery shell thanks to that. There was also a problem with runtime configuration because coreboot only does support some runtime configuration based on CMOS, but not everybody may lack this solution because the CMOS runtime configuration is dependent on the battery life on the platform. And as some may know that the CMOS memory can be influenced by cosmic rays, etc. And I have thought about reusing the Vital product data by Google, implemented by Google to store some configuration that may be changed during the firmware runtime. And so I have included in my flash map layout 2 regions, like read-only VPD and read-write VPD. In read-write VPD, I do store the default values of the runtime configuration options. And in the read-write VPD, I do store the modifiable runtime configuration options. What is more to the VPD, it also provides a utility to the user space that can freely modify either the firmware online on the SPI flash or can directly manipulate the file. So we can prepare our own binary and runtime configuration before flashing. But there were also some obstacles here. The VPD partitions must be formatted before they are propagated by coreboot and CBMM. So I have stripped the Google's VPD utility and erased all the FlashROM API code and placed under util VPD tool just to obtain some small utility to format the partitions at the end of the coreboot build. So when the config VPD is selected, I just build the tool and format the partitions. And when the binary flashed, I have already got the VPD in correct format and it's correctly propagated via CBMM hooks. I have also added a VPD library to cBIOS in order to parse some of the runtime configurations, like I can disable USB boot, I can disable enable PXE boot, or even I can disable serial console on my system, which is headless, etc. And I see also the potential of the VPD to replace entirely the old cBIOS configuration, which is based on CBFS files. Because in case of vboot and multiple CBFS partitions, it becomes just unusable because we cannot read from the target partitions as we like. The VPD is a much more convenient approach. Okay, so I would like to show you some small demo about the implementation. So I have a IPU tool here with the Magic Flash chip. Yep. And I will put it on other screen. Oh, and I have some small Debian buster on the MSATA SSD for convenience. So to show you how the SRTM works, so I have the measurements here. You can see PCRs from 0 to 7 are the PCRs of the BIOS. And I have also, oh crap, I have to, okay, and there are two binaries here already prepared for the demo. And I have already on the SPI flash the core boot ROM image, which is seen on the console. And I will now flash another firmware, which is in fact the same firmware, but I have signed it with different and randomly generated vboot keys. And as you can see, we have the Adesto chip, which was presented here. And currently, there is no lock applied. So we can flash entire firmware and be happy with it. So let's now try to lock our SPI flash. And I have enabled the block protection for the write protected read-only region and enabled the one-time program mode. So now the whole 6 megabytes region, which I presented here, is now locked permanently. So if we would like to flash the old core boot which I have earlier, let's say I will flash the WPRO region. It says that the block protection could not be disabled already. And there should be errors that the SPI flash could not be reached with some sectors. Okay, this will loop for 5 or more times in order to check for different use functions, but it's not necessary to wait for the final output. So now let's try to power off and unplug the power supply. It should now forget all the information we have got. So typically, if we would have the write protecting screw, it should disable the lock entirely. And if I plug the supply, we will still have the flash lock there because it is one-time programmable mode. And if we try again, the write protected read-only region to flash, it will still fail. Okay, so I would like to show you the last thing, the recovery kernel also. So I will just overwrite the read-write sections. In order to force the recovery mode. And as we see, these regions are still readable, as we will see, of course. And there we go, already verifying. And let's reboot. The system will reboot itself 2 times because it will find that first partition is untrusted, second partition is untrusted, and now in the third boot I can go to recovery. And there you go. We have recovery mode, we have flash on here, we have CBMM to check the logs, GPG for importing some keys or verifying signatures. We have DHCP also to get network configuration, etc. We have various ways to download the firmware and flash it back to bring the platform to the trusted state. Okay, so that would be it as for the demo. And okay. And I will thank you for your attention. And if you have any questions, oh, I missed one slide. The future improvements, sorry. So there are still some things to do, like implementing the C-environment boot block for the AMD 16H family. I still need to prepare some generic payload to modify bootloader and VPD, like in the proprietary UEFI BIOSes, also for user convenience. Port all the cBIOS runtime options to VPD. There is still to do work with maintaining the chain of trust until the OS, because there is no currently known implementation that would prolong the chain of trust with TPM 2.0 from the bootloader, like grab to the kernel. There is, of course, the trusted grab, but it only supports TPM 1.2. And there are a few issues with the TPM 2.0 in Corn boot. For example, all the logs for now are stored in the TCPA table, which is a table that points to a memory that contains a log area for TPM 1.2. The CPM utility can print TCPA logs, but not TPM2 logs. And I think it is a bug, but cBIOS just starts writing TPM2 logs at the start of the region, regardless there are any entries present there or not. And the TPM2 logs have also different format than those from TPM 1.2. So core boot should implement a correct format for the TPM2 logs also. And I started to do some work on automatic disk encryption, decryption with TPM 2.0, but for now I had run into a bunch of issues. Like I have used implementation based on Clevis, which is a framework for attestation and storing secrets. And it looks like there is some race in the Drake that does not allow to hook the Clevis into the password prompt set. So now question and answers. And thank you for attention.
I'm just a bit confused of the usage of vboot instead of just like finalizing the initialization of the chipset. Why is it needed to actually lock?
vboot does not do the chipset initialization. It is only a software that provides cryptographic operations and integrates into a stack that allows verify each executed component before it is executed. So it like verifies the firmware that is loaded from the read-write partitions. It is of course digitally signed by the keys that are generated also by vboot libraries. Okay.
Right, then thank you very much.
Thank you.